In this video, I'm going to show how we can use TensorFlow and Keras in Python to train and use a sequential neural network, which is the most basic format of a neural network, to classify images. Make sure that you have successfully installed both Keras and TensorFlow on your machine. If you need any guidance on that, make sure that you watch the video in the description. Once you have installed the TensorFlow and Keras, when you want to start a Jupyter notebook, you have to make sure that the applications is on the environment that you have installed the TensorFlow on. And if you look at the previous video, you've noticed that the environment that I've installed TensorFlow and Keras is called tf-new, and that is where I am going to run my Jupyter notebook. Now here it says it's already installed in this environment. That's why it says launch here. In your case, most likely it says install. So you have to first install it and then launch Jupyter Notebook within the new environment that you have installed. The example that I'm going to cover in this video comes from the book by Ariel Geron, the Hands-on Machine Learning with Scikit-Learn, Keras and Tensorflow. And that is described in chapter 10 of this book, dealing with classifying fashion items that are included in the MNIST fashion dataset. And that dataset includes thousands of images of different clothing items, specifically 10 different clothing items. And the purpose here is to classify each image to the correct group that it belongs to. For example, you show a picture of a t-shirt and the computer can say that it is a t-shirt, or when you show a picture of, say, sneakers, the computer say that it is a pair of sneakers. And because the items are more diverse than the previous example of image recognition that we did using the logit function, and that was the recognition of handwritten digits, the linear models that we've focused on so far do not do a good job when it comes to classifying images of clothing items. Therefore, it is a really good opportunity for the neural networks to shine. In this example, we're going to cover the most basic form of neural networks, namely sequential networks, and then we'll take it from there. All right, so once you've opened the Jupyter Notebook, create the Jupyter Notebook wherever you want. So I'm going to create a file on my desktop and I'm going to call it sequential neural networks. All right. Now, before we begin, the very important thing that you have to do here is to make sure that the common libraries that we used to use when doing machine learning with Python are installed in your environment, because note that you are using a new environment here, and previous libraries such as Matplotlib, Seaborn, and Pandas, and even Scikit-Learn are not necessarily installed here. So go one by one and install them here. So for example, if you want to install Matplotlib, you have to say pip install matplotlib, and I've already installed this, so it will go ahead and say that you have these packages for me. So you say requirement already satisfied, but in your case, most likely it will start downloading the packages and install them. You have to do the same for Seaborn, because we are going to use Seaborn as well. So pip install Seaborn, and it says already satisfied because we have it here. Do it for Pandas as well. It is already satisfied. And the other thing that you have to do is to install Scikit-Learn. So that is a little bit different code. So pip install -u and scikit-learn Learn. Again, it's already installed on my computer. And then the last thing that is extremely important for you to do before you run the neural networks on Jupyter is to run this code that I'm going to show you. And what it does is that it prevents the notebook kernel from dying in neural networks. So otherwise, if you don't run this code, something happens. To be honest with you, I don't know, but that would lead to Jupyter to crash. So go ahead and type in conda, C-O-N-D-A, install -c conda -forge, N-O-M-K-L. So I did a lot of internet search and came across this solution. It works perfectly. Just believe me and run this code. And it takes a while. Again, on my computer is already installed. On your computer, it will download a bunch of files and install this thing, but then it says you're done. And now you are ready to start your actual coding. So before I do that, I'm going to delete this part and then start by importing TensorFlow. So import TensorFlow as TF, and then from TensorFlow, import Keras. And I'm going to also import my usual libraries. So from matplotlib.pyplot, what am I doing? Import matplotlib.pyplot as plt, import numpy as np, and import pandas as pd. That's everything you need. All right, now the very first thing that you have to do is to go ahead and import the fashion MNIST dataset that we are going to analyze here. Luckily, this is a pre-imported or pre-built dataset within Keras, so you don't need to download it from somewhere else, although it is also available on Kaggle, but we don't need to import it from Kaggle. So we can go ahead and say keras.datasets.fashion_MNIST. And this is the dataset that we are actually going to import, and we are going to give it a name. I'm going to call it fashion, right? So fashion is going to be equal to this. Let's run it. And then because this is already pre-built inside Keras, the training and testing data sets are predetermined. So unlike previous instances where we had to go and import train test to split and create our own training and testing data sets, both for features and outcomes, we don't need to do that here. So we can just say X train and Y train, and also X_test and Y_test are equal to fashion. And this fashion now is referring to what we have typed in above, dot load_data. Make sure that you open and close the parentheses. Load. All right. Let's take a look at the shape of the datasets that we have here. So xtrain.shape, and you would see that there are 60,000 observations in this data set, and each observation is a 28 by 28 matrix, just like what we had before in the digit recognition data set. The only difference is that here we already have them in a matrix, a 2 by 2 matrix format, whereas previously they were in a 784 array. So they were one-dimensional. Now they are reshaped into a two-dimensional matrix. And if I do the X test.shape, you would see that there are 10,000 observations in the testing dataset. Now, before I continue, I want to do a very, very important yet very simple transformation here, and that is to normalize the input features. Because right now the features are each the RGB values ranging from 0 to 255, right? And what I want to do is to divide every single value to 255 so that everything is going to range between 0 and 1. Now, if you do not apply this step and skip it, your algorithm will most likely end up stuck in a local optima in which it will not be able to make correct classification, and the accuracy will be extremely low. In addition to this important reason that to avoid getting stuck in the local optima, there are some other reasons for which we almost always, before training any neural network, have to normalize the data. And the very first one is that it is very likely the data comes from different scales, and it is going to be important to normalize it so that everything is going to be comparable. And the other reason is that it would generally help with the speed of your algorithm. So you'd be able to train your machine much faster. So what I'm going to do here is to go ahead and say xtrain is equal to xtrain.astype float 32. Basically, what this does is that it goes and changes the type of the values in xtrain into float 32, and before turning them back to the xtrain object, I want them to be divided by 255, and I do the exact same thing for the xtest dataset. So now both the train and test dataset are normalized, meaning that their values are divided by the maximum possible value, which is 255. Therefore, they're all between 0 and 1. All right, let's also look at the labels dataset or the Y dataset. And you would notice that when you type in Y_train, for example, the values are digits, 9, 0, 0, 3, 0, 5, whatever. Yep. So these are not what you were expecting. You were expecting to see clothing items, right? Like t-shirts or sneakers or coats or jackets, but these are codes. So one way to figure out what these codes are is to go on Kaggle and actually search for fashion MNIST dataset. And here you would see the content of the data and the labels. So these are the actual labels here. So you know that where it says 0, it's a t-shirt, where it says 1, it's trousers, and so forth. So we can actually go ahead and copy these values and use them to rename the values in the Y dataset for further use. So what I'm going to do here is to create a new array. So I just call it class names, and I use these names as elements in this array. So I have to very quickly remove these extra things and put everything inside quotations, and make sure that you include a comma after them so that these would be considered as separate items. And just type in class names. All right, now we have this array that includes the name of the items in the classification labels dataset. And the way that it's going to be useful for us is that, say that we want to know what is in the, say, the first observation in Y train. So I can type in, for example, Y underscore train, the first observation, and it will give me 9, right? I don't know what 9 is, but if I had typed in class names and then Y train, the first observation, then it would write in ankle boots, right? So this would be a very handy tool that we have in order to translate these numbers into fashion items. And before I continue, let's take a look at our data set and see what images are there. And if you remember, for image recognition data set that we worked with for handwritten digits, we used imshow. So I'm going to use the same function here. So plt.imshow, let's say xtrain, first observation, CMAP is gray. So what I'm doing here is that I want to display the first observation in the training data set with a color map of gray. Now, the important thing to note that is because the structure of the data set is already a 28 by 28 matrix, I do not need to reshape the xtrain data set. So I can go with whatever I have here. And this is what it shows. Now, it looks like probably a pair of ankle boots, but if you want to know what the name in the label data set is, you can go ahead and actually print it. And that would be Y underscore train, first observation, and you have learned the trick here. So it's actually here. It's the first observation. And it is an ankle boot. And now we can look at other observations. And you say that this is a t-shirt. And let's say, what is observation 100? This is a bag, and so forth. The last step that we have to complete before we start training our neural network is to normalize the values of the features. And we have to normalize the input values, the feature values, most of the time that we're working with neural networks for a bunch of different reasons. The very first and most important reason is that we do not want to have our algorithm fall into a local optima, meaning that we want the algorithm to be able to find the global optima, and normalizing the input features is a really good strategy to achieve that purpose. The other reason is that in many different settings, you're working with a set of features that have very different scales. So it would be much better if you normalize all the features so that they would all be within the same scale. finally, your algorithm would converge much faster if the values of the input and features are normalized. And in order to normalize, I am going to basically do two things. The very first thing is that I am going to divide the values by the maximum possible value. And the values of the features that you're working with are RGB values. Let me remind you of that. And the RGB values, as we discussed in the handwritten digit recognition video, range between 0 to 255. So the highest value of RGB is 255. And if we want to normalize it, we just divide it by 255. Therefore, we are going to ensure that the values of our data set are going to range between 0 and 1 as the maximum. And then the other thing that I would do is that I change the type of the input values, of the feature values, to float, so that I could have, decimals. So basically what I do is that I say x_train is equal to x_train dot as type, or as type, float 32, and then divided by 255. I do the same for the x test. And then I would be ready to go. I have to rerun the algorithm from the beginning. Okay, now everything's fine. So in order to create a sequential neural network, what I'm going to do is to call Keras. So I could type in keras.models.sequential. Make sure that sequential, the S is capital. And then I give it a name. I just call it SNN, short for sequential neural networks, right? So SNN would be referring to keras.models.sequential. Before I continue, let's review how a sequential neural network looks like. Well, in a sequential neural network, you start by an input layer that is going to have m nodes, and each node is going to be storing the value of each of your features. Now, the way that a sequential neural network is modeled in Keras is that you have to model each layer independently and in sequence. So we have to start with the first input layer. And let's think about how many nodes we would need in the input layer. We have 784 features because we have 784 pixels. Remember, each image is a 28 by 28 matrix. Therefore, there are going to be 784 cells that each of them has a particular value, and they would be representing a feature in your data set. Therefore, we need an input layer that has 784 nodes. So how are we going to model that? We can go ahead and say model.add. Okay, what do you want to add to your model? And here, because the name of the model is SNN, we have to say SNN.add keras.layers.flatten input shape is equal to 28 by 28. All right, now let's take a look at what I've done here. I am going to add an input layer, therefore, to my model, which is called SNN. Therefore, I just type in SNN.add. Now, when I want to add my input layer, I told you that we need to have 784 features. However, the dataset that we're working with is in a matrix format. So the observations are in a 28 by 28 two-dimensional matrix format. What we are going to do with this flatten feature is that we are going to give it an input shape that is a 28 by 28 matrix, and then it will flatten them into a one-dimensional array of 784. Okay, so try to visualize that you are pressing a cube into a plate, into a one dimension, all right? Or that is how the 28 by 28 matrix is going to be transformed into a one-dimensional array of 784. Now we have to go and add our first hidden layer. Again, this image would help us to visualize the process a little bit better. So we just created the first layer that had enough nodes to read all the features that we had in our 784 nodes. Now what we are going to do is to create the middle layer, the very first middle layer. And there are two important things that we have to consider. The first one is the number of nodes that we are going to have in the middle. And then the second one is the type of the connections between the nodes. So the number of arrows that go from each node in the input layer to each node in the output layer. What we're going to do is to exactly model what you see on the screen, which is a dense network, meaning that there is a connection between every input layer to every node in the hidden layer, the first hidden layer. The other thing that we have to decide here is how the first layer is going to transform the weighted sum that goes to each of these nodes. So as you can imagine that in the first node, you're going to have a weighted sum that is going to be W multiplied by X of all these arrows that get into it. But that should be transformed to an output somehow. And here we're going to use a Relu activation function. And Relu stands for rectified linear unit, which basically is going to return 0 if the input is less than 0, and it's going to return the actual input if the input is larger than 0. So if the input is, say, -5, the output is going to be 0, but if the input is 5, the output is going to be 5. So I can actually go ahead and type in snn.add, again, keras.layers.dense, because we are going to be connecting every node in this layer to the previous one. And then I'm going to choose 300 as the number of the nodes, and the activation function is going to be Relu. What I'm going to do is that I am going to add the second hidden layer as well. And for the second hidden layer, again, it's going to be, because it's a dense network, it's going to be connected, everything's going to be connected. However, the number of the nodes, instead of 300, I'm going to reduce it down to 100. The activation remains to be the same. So I would go ahead and copy this, paste it down here. Instead of 300, I'm going to have 100. Finally, we have to decide about our output layer. Our output layer is going to include the nodes that are going to contain the values for the classes that we have. And we have to decide how many nodes we need here, and that should correspond to the number of classes that we have. And remember, we had 10 items, 10 clothing items. Therefore, we need 10 nodes in the output layer. each of these nodes is going to ultimately store a value between 0 and 1, depicting the probability that the agent or the machine learning algorithm thinks that the input belongs to that class. So we are going to have 10 nodes in the output layer. And then the other thing is about the activation function that we would use here, because we are going to have exclusive classes, because an item can only belong to one class. A shoe can only be a shoe, it cannot be a dress. We have to use the softmax activation function. So the way that it works is that I can just copy and paste it here, change it from 300 to 10, and the activation should be softmax. Okay, now let's run it. And once it's run, we can just type in model.summary to take a look at what we have here. Sorry, just type in snn.summary. Okay, now this would give you an overview of your neural network. So we have one input layer that has 784 nodes. Then we have our first hidden layer that has 300 nodes. And then the other hidden layer, which has 100 nodes. And finally, the output node. The last column shows the parameters. So one thing that it is interesting to look at is the number of parameters in here. And it says 235,500. Where does this come from? Well, remember, you had 784 nodes in the input layer, and every node was connected to every node in the first dense layer that had 300 nodes. So 784 multiplied by 300 would give you 235,200. The remaining 300 comes from the biases, or the constants that are going to be added. So 784 multiplied by 300 plus the additional 300 would give you this number. Now you can actually give a name to the layers that you have in your model. So let's first of all type in snn.layers, and it would give you the layers that your model has, but you can give it a name. So I, for example, can say hidden one is equal to snn.layers 1, and that would be my first hidden layer, is now going to be called hidden 1. Let me just run it. And if you want to look at the weights and biases that are in your network, you can just type in weights biases is equal to here hidden 1 dot get weights. And then if you want the weights, you just type in weights and it gives you an array. Now, to understand what it is, you have to pay attention that you have not trained your model yet. Therefore, the weights are going to be a bunch of random values that are just initially assigned to each of the arrows. You can also look at the biases, and that would be 300 zeros. So these are the initial constants that the algorithm has assigned. These would be updated once you run the model. So I will come back and run this code once again after I have run the algorithm, and you would see that these biases will no longer be 0, and the values of the weights will obviously be different. Now, before we fit the model, we have to decide about a bunch of other things. The very first one is to decide the cost function that we want to minimize. And if you remember our discussion about OLS regression, we said that in OLS, the cost function that we are going to minimize is the sum of the squared errors, right? in neural networks, you can have many different types of loss functions, and the one that you're going to use here is the sparse categorical cross entropy. Why are we using sparse categorical? It is categorical because we have a classification into multi-classes, so 10 different classes, therefore we are going to use categorical, and then it is a sparse because each item belongs to one class, all right? So the loss function that we're going to use is going to be the loss categorical entropy. Let me start typing in, and then I'll explain as I go forward. So we can say snn.compile, and first define the loss function or the cost function, and that is going to be sparse categorical cross entropy. Now, the other thing that we have to think about is the algorithm by which you want your machine learning agent to minimize the loss function. And in the videos, we talked about gradient descent, and this is what we are going to use. So we can say optimizer is equal to SGD for stochastic gradient descent. And then we can also look at the metrics. Here we can say accuracy. All right. So this is how the model is going to be compiled. And now you are ready to fit your model. So you can go ahead and type in snn.fit. Then you have X train and Y train. Now, one additional option that you can define here is the number of epochs, or the number of passes that you want to go through your training data set. Here, basically, you are splitting your training data into whatever number of epochs that you define here, and then the training is going to happen sequentially. So here we go with 30, and I can run the model right away, but I am going to put this into a new object called history, because I'm going to plot the performance over different epochs and how it improves. Therefore, I need to have the values stored in history. Now let's run it. And it starts running. And depending on how powerful your computer is, you would get different run times. So what is happening here is that, as you can see, the algorithm is running, and it is giving me the performance measures based on accuracy for every time that it runs. So the first time, it had an accuracy of 14%, and as it goes, you see that the accuracy is improving. So now it's only giving me a 59% accuracy, which is not good at all. Let me run it again. And it starts from the 59%, and it continues from there. So this time we're at 69%, and it should go as high as 90 or 92%. So I'm going to run it again. And remember, every time that you run it, the latest values of weights and biases are going to be assigned as initial values, and it's going to start from there. So it should be a continuous improvement. And you may get lucky, and your very first accuracy in the first run may be starting around, say, 50% or even 70%. It is because of those random assignment of initial values for biases and weights, right? I got particularly unlucky this time that I have to run it multiple times in order to improve the accuracy, but it should not be like that. Usually, even with one run, you would get about 90%. So because I'm not very successful in improving my accuracy using the SGD optimizer, what I'm going to do is that I'm going to choose a alternative optimizer called Atom, and that works much better than SGD. Then the other thing that I want to do is that I want to change the epochs from 30 to 5 so that it just runs faster. And with Atom, you would see that the accuracy is significantly better. So it starts by 86% and goes to 88%. And remember, I reduced the number of epochs from 30 to 5 so that it just would run a little bit faster. I want to see if I can increase it from 88% to something higher. So we are 89%. Let's just run it one last time. And we can get 90% accuracy, which is really good. Now, what you can do is to evaluate your model on your testing data set. So you can type in the name of your model. In my case, it's called SNN, evaluate. Then give the X test and Y test data set's name to see how it does on your testing data set, and you see that you get 88%, which is pretty good. Now, one thing that you can do is that you can plot the loss and accuracy improvement in your model as it goes through different passes into the data by using the data frame first to visualize the content in the history object. Okay, and then we want to say plt.grid to be true, plt.gca, and then GCA stands for get the current access, and we put a upper bound and lower bound for our y-axis. Then we go ahead and say plt.show, and we get this for our accuracy and loss, which does not show any improvement over the different 5 passes that we go through. And the reason is that there is not much improvement. So it starts from 0.8991 and goes to 0.9063. Now, if I change this 5 to the, say, instead of 30, I go with 20, so that it just goes faster, and I change this back to SGD, just so you can see how the plot looks like. And see, because even though I am going with the SGD, because the model is already trained and it uses the best values in the last run as initial values in the next run, the accuracy starts from 89%, and you know it is again it's not gonna improve that much. So let me stop this, and what I'm going to do is that I go back up and redefine my model and recompile it so that it starts with random values for weights and biases. So it starts from 0.9 and it continues from there. You know what? I think I figured out why it's not converging to the high accuracy rate with the SGD algorithm, and that is because I had forgotten that I had already put in the normalization once before, so I normalized it twice, meaning that I divided that by 255 once and then divided it by 255 again, and that has messed things up. So I'm just going to delete this part, which is redundant, and then rerun the code from the top. See how it does. And now you see that even though it is SGD, the values are way better. So the problem was with my input data. There you go, I get 90% accuracy in testing, and in evaluation, I get 88%. And now, see, this is how the graph looked like before. And now this is the graph based on the SGD optimizer. And as you can see that the accuracy starts improving until it gradually plateaus and the loss function is decreasing. And if I go back up and I say, now print the biases again, how about weights? You see that the values of the biases are very different from 0. That is, these are the trained values for the biases. Okay, now that we are happy with our trained model, we have to use it to make some predictions. And it is so simple. We can go and type in predict y, and it would be SNN, which is the name of the model, predict X test. So what it does here is it's going to basically go ahead and make prediction based on the values in the features of the testing data set and put those values in the object called predict Y. So let's do this, and then let's print it to see how they look like. And this is how they look like. And the very first thing to notice is that they are all between 0 and 1. So none of them is less than 0 and or larger than 1, obviously, because these are the probabilities. So to make it a little bit easier, let's round it up so that you can see much better. All right, so these are the predictions, and as you can see that almost all of them are 0 except the ones that are almost 1, right? 0.99%, or here's 100%, 98%, 95%, and so forth. And the reason that they appear to be like this is because we use the softmax activation function for the output layer. And if you remember, I mentioned that we use that because we want to put each item in only one class exclusively. Now, the task is to somehow change these numbers to classes. And what I am going to do is that I am going to transform these numbers into either zeros or ones, right? And the way that it's going to work is that for each of these rows, I want to find the maximum number, in this particular case, the 98%, and see what is the location of that. This happens to be the very last one, okay? And you remember that they were numbered, so you can have 0, 1, 2, 3, all the way to 9. So here, what I want to do is to have a function that looks at this first row and tells me that the maximum value in this row is in the very last place. So the indices of the maximum numbers are going to be displayed. And that is by the argmax function in NumPy. So you can go ahead and type in np.argmax and then give the array that you're working with, and also type in axis is equal to 1. And we want this to be stored in a new object that we're going to call it predict class. So let's run it, and then once I print it, you see that you have 9, 2, and so forth. Now, if you take a look, you would see that for the first argument in this line, the maximum number was in the 9th position, so 98%, and you see that it returns 9 for you here. How about the second line? You see that the maximum here is the 99%, and it is in 0, 1, and 2, second position. So that is why you have 2 here. So these are going to be the classifications that the algorithm has made. And the problem is that they are, again, in numbers, but we want them to be translated into words. So we're going to use the same trick that we use in order to read the input data here as well. So, and that is going to be using NumPy again. So type in np.array, and we are going to use the array that we defined way earlier. What was the name of the array? Class names. Bring it down here. Oops. And then inside the brackets, we would put in the predict class. And now you would see that number 9 is translated into ankle boot, number 2 is translated into pullover, and so forth. So just to visualize some of the predictions, let's take a look at the items in the testing data set. So just type in plt.imshow x_test, and let's say that the first item, but cmap gray, then we can say that print the prediction for this item is the class names which item in the class name? The one that is in the predicted class. So class name, predicted class, and make sure that you put in 1 here because you want it to be corresponding with whatever you're showing, okay? So let's run this. And you see that this is something that looks like a pullover, and the computer has correctly classified it as a pullover. Now, if you want to see many more without continuously changing the items, you can create a random item. So you can say random item is range, let's say 10,000, because we have 10,000 observations in our testing data set. And then instead of 1, you're going to have item. And here you're going to have item as well. Then you can run it multiple times. It's not defined yet because I have not imported the library here, so I have to first import it. So I'm going to go up here and say from random import rand range, and now it should run. Okay. So now that I am running it again, every time the result is something different. So this is this picture that looks like a pair of shoes or sneakers, and you see that it is being correctly classified as a sneaker. This is a sandal, and this is a shirt, and looks like a shirt. A much more formal way to look at the performance of a model is to create a confusion matrix. So I'm going to go and import the metrics from Scikit-Learn. So from Scikit-Learn, import metrics, and then create a confusion matrix. And the inputs for the confusion matrix should be the true labels, which is stored in the y-test, and the predicted labels, which in our case are going to be in the predict underscore class. So y-test and predict class. And this is going to be our confusion matrix. Let's save it into an object. So that we can plot it now. And because I'm going to use Seaborn, I'm going to import it. And now I can type in SNS.heatmap, and the data set that I'm going to use is going to be my confusion matrix. I don't want to have, I want to have the annotations, so that's why I put in true. And in the video about handwritten digits recognition, I went into every aspect of this heat map creation in very detailed way, so I'm not going to explain every part here. The format of the displaying of the numbers is going to be then this color map, I'm going to use blues, and I do not want to have the color bar. Therefore, I just type in false. And this is a preliminary view of my confusion matrix. If I want to make it a little bit better, then I'm going to add a title. Say the confusion matrix. And I type in plt.show to get rid of the additional stuff that was there that I really didn't like. And then I can put in the labels. So plt.y label is going to be actual item. And then plt.x label is going to be predicted item, or let's say classified item. So you have the actual item and the classified item. Now, the point here is that The items, both actual and predicted, are again shown in numbers, but it would be really better if we could show them in words, and we are going to use this trick using the ticks on the x and y axis. So you can type in plt.xticks, and first of all, you're going to have 10 ticks. So you're going to type in np.arrange of 10 plus 0.5. So it's going to move each tick to the middle. And the other thing that you can do is that you can go up here where you had your class names and actually use that to name the text. So copy it from there and just come down here and paste it. And you see that these numbers are here. Now the problem is that the size of the plot is not really good, and you can fix that as well by using the fix size. So plt.figure, and then fix size is equal to, let's say, 10 and 10. So it's a much larger one, and then you can actually read them. You can do the exact same thing for the y ticks. So instead of x ticks, you're going to have y ticks. And now you have the actual label of the items rather than their digits. All right, now this is a very nice way of displaying the performance of your model. And when you look at the confusion matrix, you would see that for t-shirt and top, for the items that are truly t-shirt, they're very likely to be misclassified as shirt. So there are 142 instances of that, which is pretty understandable, right? The computer confuses a t-shirt with a shirt. How about the pullover? The other mostly confused item is a coat. So a coat is mistakenly classified as a pullover. And then what else? Here you have a shirt that is classified as a t-shirt incorrectly. Sometimes it is classified as a coat or a pullover. Otherwise, the algorithm is doing a pretty nice